carrier. Okay, thank you. It's no problem. And as could be hydrogen or a product that contains hydrogen. And why we select the ammonia? The ARENHA is focusing in the ammonia as a green hydrogen carrier. And we deal with all the value chains from power to ammonia and ammonia to use. Direct use, or we also doing decomposing afterwards. So in all these fields, we do development on materials and also new designs and integrating them into several systems. So to show if possible the flexibility, the security, and the storage utilization of this ammonia as energy storage. Why ammonia? Ammonia is something that is not, maybe I would say a century or more. I would say this already, we know how to deal with. There are standards, and for one side, it has high volumenic energy density. It's the first one between the non-zero carbon fuels, let's put it this way, where you can have a higher amount of hydrogen. Has a relatively low cost, but this low cost depends on the situation also. They are fluctuation. Easy to liquefy as you compare with hydrogen. Hydrogen, you have to go to cryogenic condition. With ammonia, atmosphere, I think you have to go -33, -35 degrees. For 8 bars, I think you can have a room temperature. So it's more easy than going to hydrogen cryogenic temperature for hydrogen. And also is easy to store and transport, and it's carbon free. That's the main thing. I think you have listened today that there are many initiatives to develop power to methanol as well, but also power to ammonia. So here in the project, we deal with all the value chains. We develop materials and processes for green hydrogen production, but also for green nitrogen and ammonia production, a lower TRL, I would say. Then we have a group who's dealing with ammonia synthesis. Also, for nitrogen storage, also we do some activity in solid state storage. And then we have the direct use of ammonia that could be direct use for having power from generation for using ammonia in a solid or charcoal cell, or using the ammonia in internal combustion engines. And in addition, we think, okay, let's do the cracking of the ammonia to get hydrogen to be used in a PEM fuel cell or for mobility, also for industries where it's hard to abate the CO2 emissions. And we have four prototypes. There are two stack modules prototypes at 5 kilowatts, and they are solid oxide electrolyzers. Then we have the prototype to produce 10 kilograms of ammonia per day with ammonia synthesis loop, where we have also a sorbent to improve the ammonia synthesis. Then we have a prototype for doing the ammonia cracking and producing 10 normal cubic meters per hour pure hydrogen. There was the prototype that you will have more information during this event about the different prototypes. And besides to this, we also do some life cycle analysis, cost analysis, and safety analysis on the ammonia as energy carrier in the different prototypes. And the consortium is composed by 11 partners from 7 countries. We have 45 of them are industry, and we have the other 6 others are research and technology centers and or universities. So here's a brief summary for the green hydrogen production. We have 2 solid oxide electrolyzers developed by Elcogen and Fraunhofer LTS. Then we have the Danish Technology University has been working in developing solvents for ammonia storage or for the solvent in the ammonia synthesis loop. And UCRI has been involved in developing catalysts for the ammonia synthesis. And then Proton Ventures is the entity, is a company who has designed the prototype for ammonia synthesis, synthesis loop. And then Dr. Yu has also worked on the solid storage of ammonia. And then for the cracking, this mainly Tecnalia developing membranes and going more in a lab scale, testing as a concept of membrane reactor. And H2Side was the company who has developed the cracker system. And finally, we have also the Fraunhofer IKTS has been working in using direct use of ammonia and solid oxide cells for power generation, and Stellantis, that is the group Peugeot and I think emerging also another automotive company that has been working in studying the direct use of ammonia in internal combustion chains, studying the mixing of hydrogen and ammonia to increase the working condition of the chain. And then we have the testing of the different prototypes. So why? Because we are working these projects. We want to develop more efficient and cheaper long-term energy storage in form of green ammonia. Also, we use ammonia as a hydrogen carrier, so we can use it for mobility, transport, or industrial that are difficult to decarbonize, because the idea now is to clean energy transition, to have more electrify all the society, let's put it this way, also the industry. But and for the maritime sector, for instance, you can also have they are working using ammonia for decarbonize the maritime sector. And the idea is also to increase the renewable shares in the grid to large scale energy storage, and to have a static position for Europe regarding the energy storage technologies. And a main point is also that has been raised this last years is to decrease energy import dependency by using ammonia to diversify energy supply from other countries than instead of Russia for natural gas, for instance, in Germany. Is a way to diversify, to do both things, decarbonize and diversify the energy supply. There are already corridors in Japan also to have ammonia from Australia, or also corridors here in Morocco, from Spain, also for Mars that they are looking for, or from Chile also, so that to have ammonia coming from there. And also you have you diversify, so you also secure a clean supply of energy. And besides this is behind this is also the energy green deal, so to go to a low carbon society and replacing all the fuels, fossil fuels in different industries and transport sectors for reducing the CO2 emission. So I will go some hints about the different activities, but you will have more details afterwards. So there were some for the solid oxide electrolyzer developed with Alcogen. There were new materials and hydrogen electroactive layers, sense of hydrogen electroactive layer microstructures, also in the other active layers. So they developed new materials, and then for these new developments, they developed the prototype. It's a small prototype, of course. And this prototype is in Fraunhofer hands for the validation. In the case of Fraunhofer, they do also the new developments on the state-of-the-art electrolyzer, solid oxide electrolyzer. And then also the stack is in here, Central National Hydrogen, for the testing. And they also did the assembly of the cells for both the Alcogen and the IKTS to have the prototype. And also this for the electrochemical green nitrogen production, there were more colleagues from DTU They did a longer test, it was around 1,500 hours of able to produce nitrogen with 98.3% of purity without degradation. And for the ammonia synthesis loop, the design was made by Proton Ventures. The catalyst they used was a iron-based commercial catalyst from Clarion, and they used a solvent developed by Danish Technology University. They have done the factory acceptance test part that the system is operational feasible. You have some drawing or figures of the prototype. They will do the test in the future. They have to define the place. They're very interested in this prototype. And then regarding the cracker, the concept here is to use the palladium-based membrane reactor technology, where you put in the same place the reaction and the separation, so to reduce the steps in the process. That means also and the different components you need. And doing this, removing the hydrogen, you are also shifting the reaction towards the products. That means you will increase the conversion at the same temperature. Maybe you will something later on. And you can work at lower temperatures due to this. And the footprint is also lower because it's unifying the different steps. That is called is a type of process intensification. So here is an example. You can see is how when it's driven by the force between the it's driven by the pressure difference between the reaction zone and the permeate. Is you see the blue dots are for the without membranes, no membrane. When you add a membrane, having 1 bar in the pressure in the permeate side, you increase the conversion. And having the vacuum means that at the end of the vacuum you have 1 bar 0.1 or 0.2 from the rotary bond. It used to be vacuum bond is not very high vacuum, 0. Maybe 0.1 or 0.2 bars, I think. And you can get 100% conversion for the in ammonia cracking. So you go from 65 to 100% conversion. Lower temperatures, you get the data conversion. Okay, okay, so for the prototype, the membranes were developed by Tecnalia. They were 52 skin palladium-based membranes and developed by electrolysis plating with an average length of 45 centimeters long, and the overall membrane area was 1 square meter. And the catalyst we used was a commercial catalyst. Here you can see some picture figures, and first the design was a high cube container where you have all the components. It's a plug and play system. And also you have to contain the attack zone. And the cracker has been operated in the National Center of Hydrogen here. And there were some training from each side, and also they were here, they were monitoring also from outside, and there was a good collaboration between the both teams. And from the SOX, we have some direct use of ammonia for power generation. There were some activities carried out by Fraunhofer AKTS, where they found that, in fact, the ammonia was cracking before arriving to the solid oxide fuel cell. Already in the heater exchange, as far as I remember for the presentation. So, but it could be interesting because then you can do this design a different way. You don't need to crack in the solid oxide fuel cell to crack the system. You could be more simpler, or more compact as you want. So they are the same membranes you can use for solid oxide electrolyzer. They can be used for solid oxide fuel cells. You have further information later on. And finally, we have also we do modeling all the membranes permeation, also ammonia synthesis, and membrane reactors, but also we do the modeling of the overall system, mainly power to ammonia concept, and also for ammonia to hydrogen ammonia cracking. You will have information also during this event about this information. And they do some technology benchmarking and economic comparison between different production and the composition process. So, okay, finally, this is the main results. We will review now. We will draft the final report and we will do a review on this. We have already have one PhD degree on this project. This one also coming, also have been done in the facility in the front of this project. 11 scientific publications, 37 conference workshop attendance, 2 patents, 8 newsletters, and other communication materials. That's all from my side. And I will give the floor to the next speaker.
Yeah. Okay. Next speaker is Stefan Megel, sitting next to me. He is the group manager at Fraunhofer Institute in Germany, and he will be presenting their results on the solid oxide electrolyzers, together with Freddie Cook, who is also in the room, who is a research and developer at Encogen. So if you don't mind, Stefan, let me.
But I need my Estonian tall colleague here.
Yeah, he might be here in a sec.
Can you ask him?
He will come up. So, do you want to start now?
Yeah, sorry. Any questions?
No, the question would be, because we will give more details. For me, it's a similar one. We can have also questions at the but you will have questions.
That's okay, because sometimes I need more time. Especially if you see on this crowded slide that we will have a dual talk with Freddie and on my side. Thank you for the introduction. It's nice to present here in this public workshop the activities on the ammonia-fueled SOFC and the steam electrolyzers with our 2 different SOEC types, but it's more or less one prototype what we are developing, but with from different. The talk is structured into more or less 3 parts, but if you look in the details, the first thing is that we are talking about this ammonia usage. We simulate something and we make tests. The first part what I present by
Clara, sorry,
what?
I think the presentation is not sharing.
Oh, you see it.
Thank you, Jack.
Thank you so much.
You're welcome.
And then I will talk about the stack assembly and the performance in SOFC and SOEC mode. And then I will hand over to Freddie Cook. Now he's on my side. Welcome. For the Encogen activities, it's more focused on the cell development and then the short stack tests. And then I will overtake because the other thing is that we need for a prototype and for the connection to a system valuable interface, and we integrate the stacks into hot boxes. We call it stack module, and this is done by IKTS over a long time, and we use this background knowledge to design the 2 stack modules. So we integrated the MK35X stack developed by IKTS as well as the E1500 stack by Encogen. Then I will have a short conclusion. Coming now to the point, what Jose Luis also sneaked, but in the end, the usage of ammonia in a SOFC is a pretty cool thing because it has no CO2 inside. So if you have no CO or C inside the fuel, then you cannot cook. it sounds easy, but when you have CH4 or other carbon fueled SOFC operation, you every time come to the cooking problem. That's why my group from system evaluation takes some models and try different things. So we have calculated easy-driven single-line CPOX systems, and we come out that we have an efficiency of 51% DC. Mostly you need an AC converter, it's less, but anyway, a 51% is quite high with also this small single line system. But if you recycle the anode gas, then you can get higher efficiency because you have a better usage and you have a better heat integration. That mentioned that you can come to 60% of efficiency, which is really high, and you can reach this also as very small systems. The task what we had to consider was to test the ammonia inside the stack. So we had test rigs like you see on the right side. We flushed ammonia inside this test rig. We heat it up over preheaters, and then we give it to the stack. And we have seen that we crack the ammonia at stainless steel or Inconel when we are reaching 600 degrees C. So not only 5%, it's 50% of cracking was only in the pipe. No cracker material, no catalytic material inside. So that was enough to crack the ammonia. And this changed many things of the points when we go to a system evaluation. But I will come to that a little bit later. I want to end the big point here on the slide is ammonia is a perfect fuel for SOFC operation. On the next slide, I bring you exploded view of the MK355 stack. It's electrolyte supported cells supported by the chromium-based interconnect. They are pressed powder metal sintered interconnects. The development took more than 20 years or later. We also catched it in several other points, but in the end, for the last period and ARENHA period, we improved the cell, we improved the electrodes, and we optimized some stack assembly to get higher power density from the stack. Here you also see that we have an open air manifold and a closed gas manifold, so it's very easy to integrate the gas side. You only have a mica seal and you place it on an adapter plate. For the air, it will be customized, and that's why we have to make the stack module development that you have a clear interface between the system and the stack. Coming now to a performance map. So we are doing UI curves at the stack level because the temperature is every time different. All of the points are measured in stable, constant operation points, more than 2 hours stable, and then you can come to this point from everywhere else. So if you have a stable temperature region over the stack, you will get exactly that cross when you operate with ammonia. And I have also integrated some dots, and this is a different thing. It's the mix when you get a 100% crack of ammonia. So we flush it by hydrogen and nitrogen mixture. But from a tensor stack, you get at high current density about 400 watt. It means 40 watt per cells. And at part load, you can select the current density and you get the reasonable power output. So it's very flexible, and also the efficiency at part load is quite high. This is more or less an advantage of the SOFC system. The other thing is that we have over a wide fuel utilization, more or less no power loss. We can operate them till 80% fuel utilization. And last but not least, look to the difference between the dots and the cross. It's marginal, it's less than 5%. And that was the thing where we get curious about these results. And we come in 1.5 years of R&D and testing that the cracking takes place also inside the pipes, what we already mentioned. And for the last year, we consider this as a topic for R&D, that we can move to materials for heat exchanger, which are still the cracker. So for a system, you need the afterburner and you need the heat exchanger. And if the heat exchanger is the cracker and you can integrate the afterburner inside the heat exchanger, you have a really compact system. And you can do it very small, that you can handle this perfectly and get a high efficiency. With this, I also want to mention that we are looking also to big systems. So we think that ammonia SOFC is a good application for marine propulsion or marine usage for propulsion on ships. So in the megawatt scale, and that would be one of the big applications for ammonia. Now, the diagram looks more or less the same, but it's completely different. The only equalizing point is we use the same stack. And this is that what is another advantage. We do not have an electrolyzer stack and the SOFC stack. We are using the SOFC stack equal in the other direction as an electrolyzer. That reduces costs because you have one mass product and can produce it for all of the applications. Here you see the stack power of the tensile stack over the temperature, and the crosses are the current density. And it ranges from very small current densities to high current densities. Our standard before the ARENHA project was the 600 milliamps per square centimeter. We increased this to 700 milliamps per square centimeter by optimizing the connection to the stack and the electrolyte as well as the electrodes. Please remember, we are taking roughly 120 watts to convert the steam into hydrogen. I need this later when we try to calculate the power of the stack module. Let me conclude the first topic of the stack. We have stacks which can operate in SOFC and SOEC mode. In SOEC, we have roughly 120 watts, which we can turn into hydrogen. We increased the ability to pull power inside over the last decades. For SOFC, we reached very good power output is 40 watt per cell. And we find the point why we have comparable values to the pure hydrogen mixture. The reason was that we already cracked the ammonia easily at stainless steel surface over 600 degrees C. And this can be used perfectly to get a very compact system where the heat exchanger and the afterburner can be coupled and you don't need any cracker anymore. The pre-last point, what I didn't mention is we are operating at 830 degrees C or 800 to 860 degrees C. We have a very wide operation window, and the nitrification is less when you operate at very high temperature. You go to lower temperature, the nitrification can be a problem. We didn't see any problems also over long-term tests of 1,000 hours and post-mortem analysis. We have something on our list. We want to do more stack tests to get more in detail about the ammonia, which is still cracked inside before the stack. And we will do also a presentation after we ended this project here in Stockholm about this. With this, I want to hand over to Freddy, that you can overtake the part for the LPGen cell development and stacks. Thank you.
So LPGen's part in this project was mainly to work on the hydrogen production development. The stack that will electrolyze water into hydrogen that will be used for the ammonia production in the Denmark facility. So our premise was to keep the cell structure mostly the same that Elcogen is known for, but try to add in extra like some materials, experimental materials into the electrodes, both the air and fuel electrodes, to see if we can increase the performance in electrolysis mode. And we did have some positive results. Finally, we saw that adding iron into the hydrogen electrofuel active layer did give substantial increases in performance of the stack. So this we took further into short stack tests, meaning some of the other positive results were also put into the same stack as the cells modified with iron, along with the reference cells. And here we see that although in the stack environment, the cell with the iron enhanced active electrode did not, after the initial deactivation, give a substantially better performance. It did, however, still stabilized faster than the reference cell, which means that if used for longer than 1000 hours, it could end up being still performing better than the reference cell. Going forward from this experiment and from previous experiments showing that a thicker active layer could also yield better performance in electrolysis mode, especially at lower temperatures that the Elcogen stack works at, we opted to make these changes into the experimental cells for the ARENHA project. And we constructed a demo stack of this. So this is a 5 kilowatt Elcogen stack made for electrolysis during the ARENHA project. And it only has the iron doped fuel cells that are also that we assembled successfully and made a initial performance performance test after conditioning. And the performance after conditioning performance results were along the lines that we expect. So nothing a lot different from here, but we will see in the demo finally if we actually see any performance gains in electrolysis mode as well. And this is it from Elcogen.
Thank you, Freddy. So we have now two stack technology, one on the high temperature region and one on the lower temperature region. But we package this into stack modules to get clear interfaces to the system. And that was the task from Fraunhofer. I'm responsible for this activity for more than 10 years. And we start with the MK355 stack, so it was a high temperature stack made or designed by Fraunhofer. And we started in the early stage that we managed to have an air box to feed the air inside the stack and adapter plate where we have a clear interface to the gas side. We have insulation around and we have the compression system on top. The design was very easy because we had no big boundary conditions where we have to fit in. It was every time a test rig where we plan to test. So prototype stars. On the middle page you see a picture. There's a closed air box. There are stabilizers because sometimes we have some overpressure. There are compensators to compensate thermal expansion and to feed through the compression. If you look inside this airbox, there's many of sensing wires and thermocouples. You see here the adapter plate with the pipes, and we close this. And this is our, I will say, daily business, how we do stack module testing. Here you see it closed And then you will see it also here at the guided tour at the lab. There's this MK355 cell stack module standing there and waiting for connection to the test rig. The assembly was without problems because we've done it several times in different sizes. We have test rigs where we can commission the stack modules, and we have done it, and I selected only a small amount of data, what I want to show you here, and this is the SOFC operation at our reference point. Our reference point in SOFC operation is set also at the ceiling from the stack. Then we have a reference point at the stack module, and we compare this. And we are very happy about the integration of the stack because the reference point means exactly that what we get from the ceiling. But step by step here on this slide, you see constant operation point of 3 different things. One is the 75% gas conversion. The other is the 60% gas conversion, and the last one is the 80%. There is a change because there is a dependency on the fuel utilization. But it's every time homogeneous, and that shows us that we have a very good gas distribution, no leakages, and all the cells operating by the same. On the right scale, you see the average of the cell voltage. On the left scale, you see the package voltage because we are packaging 6 cells in one package. So we have 10 voltage measurements inside. For us, there are very good results. We can catch one number in SOFC mode. We have 1.7 kilowatt in our reference case. So we are exactly on the line, like I've shown you in the tensile stack, where we have the 275 milliamps per square centimeter. So perfectly met this point here also in the stack module. For ARENHA, we are focusing on the electrolyzer prototype. So we have to turn the current in the other direction with the same stack module. Our test rig has no steam evaporator. They have a bubbler. So you need carrying gas to get the steam inside the stack module, and this is a problem. Fortunately, we can do co-electrolyzers. Co-electrolyzers means that we have CO2 and steam and split both of them. So the stack don't care about the molecules. They transfer the oxygen ion. And it comes from CO2 or it comes from steam. That's a favor. That's why we can test it. This stack also in co-electrolyzer mode with a regular bubbler. And we get out at minus 50 amps. It's part load. What we pull in nearly 4 kilowatt. So nearly 4 kilowatt at 50 amps. This is part load, but we could not go higher because of the evaporator. For ARENHA, it doesn't count too much, but if you want to couple the next instead of a Haber-Bosch process, Fischer-Tropsch, you need H2C of 2, so it's perfectly for Fischer-Tropsch, so you can make jet fuel afterwards with this synthesis gas what you get out of the stack. Now I pleased you to remember about the SOEC performance map, 120 watt per cell. We have 60 cells inside. That means at full load point of our operation window, we can put in 7 kilowatt. It's much more than we predicted for our coupling, where we want to have 25 standard liter per minute of hydrogen in our prototype. So we will operate them at part load or lower temperature. So we will use the complete operation window, and the colleagues around Christina will do this in the next week to have a proper alignment also on their test. Now we are coming to the Alcogen stack integration. I think you don't see so much a difference, but the stack is different. We are using the same connections because we want to test the same stack modules in one test rig without changing flanges, adapters, and so on. So it's a second stack module what we produced. with the same interface. Also on that side, we had no problems. There were good communication before on the CAD level, and when you fix the CAD and don't make any changes, mostly it fits. And we get help from the Estonia as well as the Finnish colleagues from Elcogen. It was fun, and also the CNH2 people were visiting Dresden. It was nice come together, and that's also one of that I like the European projects. Unfortunately, we could not start the test here at CNH2. We decided to leave it at Dresden, and we will start this commissioning in Dresden in parallel to that commissioning of the other stack of IKTS stack here at CNH2. That will be done also in the next days, so you get it at the final reports that we will hopefully get a good result. Let me conclude my talk. We developed under the umbrella of ARENHA a little bit the cells. We increased the current density, and we are coming from a stable platform of the MK35X stack development over the last 20 years. We can convert 120 watt per cell into hydrogen. We have a special operation point mentioned. It's 115 watt per cell at 800 degrees C, and there's high current density of minus 700 milliamps per square centimeter at a reasonable gas conversion. I mentioned that we have a very wide operation window, but the operation window is at high temperature. It's higher than 750 degrees, and it's topped at the 860. So if you degrade in stack, you have the possibility to start at low temperature, and then you degrade, and then you will end up at 40,000 hours or more at 860 degrees with the same performance, with the same power inlet for producing. We designed, assembled, commissioned 60 cell stack module. We will easily produce 25 standard liter per minute hydrogen at CNH2, and this will be the entrance for the Haber-Bosch. We couple, but at CNH2 there will be only a test rig. We will couple the two prototypes a little bit later or in simulation mode. Therefore, we need these results, and hopefully we conclude the balance. From Elcogen, I also want to conclude. In the end, they developed cells with new materials, with new electrodes, with the addition of iron, which is a good favor for reactivity. They increased the performance. The short stack tests were also very positive, and also this stabilization phase will change, but it's marginal. If you look to 40,000 hours, it's only in the first 1,000 hours. Elcogen assembled a stack and had finally commissioned it in SOFC mode, and we assembled the stack module and will do the commissioning in SOFC as well as in SOEC mode, and then we will have a good closing of the ARENHA project. Unfortunately, some months of extension, but the results are quite good, and it was, in my opinion, a success to work together, especially this two-stack developer having in one project. It's not so often. I think I have some minutes left to keep another slide. Please give me the 5 minutes.
Yeah, it's fine. It's fine.
Can we pose you a question from someone online? Yes, can I pass you a question? It's Mr. Feng from Sungrow Europe in Germany, and he's wondering, in your opinion, is fueling solar oxide fuel cells with ammonia, could it have any negative impact on it, for example, on any catalyst, nickel catalyst or anything?
Okay, I think I have to answer it in 2 times. So one, I'm not the expert on catalysts. It could be that if you make cracking. I think we have experts here, but it can deactivate by nitrification also the catalysts. But I see from our tests what we have in the stack, you don't need high sophisticated catalysts. You only have heat exchanger, which is Inconel or some kind of stainless steel, and the nickel oxide surface or nickel surface is enough to crack the ammonia. And then there will be nitrification. It could be that you deactivate this surface. This will be in the future interesting when you go to SOFC systems. The other thing what I didn't mention, when you go for internal combustion engine, you have the problem with the slip of ammonia. So you have 1 or 2%, you have to afterburn it, so you have to deactivate the ammonia. At the SOFC outlet, there's no ammonia. So there's enough nickel at high temperature, especially at our 800 degrees C or more. There's no ammonia inside. You could not find traces. And this is a real advantage for usage of ammonia inside an SOFC for electrical generation. Thank you for the question. I hope I answered it
I
first.
think Freddy wants to.
I actually have something to add to this. There have been actually studies using ammonia directly on solid oxide fuel cells with nickel catalysts. And granted, if you operate at higher than 750 degrees, the ammonia will entirely crack in the support layer of the fuel cell. And when operating below 750 degrees, there is a chance of nitrification, but this is the 750 degrees is the magic number here. Above that, there have been no nitrification sites, at least in the literature that I have seen.
Thank you.
Actually made by our colleagues in Shifus.
Okay, then I will take the last two slides here for a little bit of advertising, because it's a kind of exploitation. That's why we are doing EU projects. We try to infect industry about the cool stuff what we are doing, and that was happen. We get a strategic partnership signed in March of last year with ThyssenKrupp Nucera. So I was responsible for the last 20 years for stack and stack module development, but this is our big fish. We never get such a big project. And ThyssenKrupp, perhaps you know it, it's a electrolyzer company, and it's not only electrolyzer company, I think it's the strongest electrolyzer company, and they are searching for new technologies. So they are coming from the alkaline water electrolyzers, and now they get the possibility to get the technology transfer for SOEC from Fraunhofer IKTS. I'm very proud about this. I get here some pictures from March, where my boss and the CEO of Nucera signed the contract. And on the right-hand side, we had the planning here for a facility in Arnstadt. This is in Thuringia, where IKTS have a site of 3,000 square meter. And we placed here the complete manufacturing line for 8 megawatts a year of SOEC stacks and stack modules. Going a little bit more details, these are sealing machines, these are sintering furnace for the electrolyte supported cell. This is a screen printing line with drying ability. So you get out here the complete cell, get it to the sintering, and then it comes to the stack assembly. It's only a small device here, fully automated. And then we have here a coating device for the interconnect of the protection layer. That's all. In the end, we will start this line factory acceptance tests. We'll end this factory acceptance test in April, and we will transfer this manufacturing to ThyssenKrupp Nucera, because Fraunhofer is in R&D. We cannot produce, we cannot manufacture, but ThyssenKrupp will overtake this with their own personnel and will be happy if they can produce in the next months. The capacity will reach in the end of the year. We will do at IKTS more R&D. We will improve the stacks, the stack modules, make tests, we make applications. So in the end, we will be the trigger to use the increased capacity of the stacks. In my opinion, it's absolutely successful exploitation for such EU project, but in the end, it's not only this. And I want to end it, if you are interested in using SOEC stacks or SOFC, it doesn't matter if you want to turn which gas you want to turn into electricity. The stacks are quite good. We are searching for users, we are searching for applications. So please give me an email. We will connect together with Nucera, salesperson or business developer, that we will find more strategic partner that we already. With this, I want to close my talk and thank everyone here for the auditory for listening, and thank you for coordinator. It was really great to have Jose Luis with his colleagues here, and it's a pleasure to work in such EU projects.
Thank you. Maybe there's any question here from the audience? Don't have questions. The business fair. Lucky you. So
We saved 7 minutes.
yeah, let's move to I think it's change. Now you can stay. It's change. Then it's
I don't. So we have now, I'm not sure if she is, sorry. Sorry, yeah. Yeah. Next. Will be. Let me put you. Yes, let me present Ms. Chen Liang from Proton Ventures. She's gonna tell us everything about their developments in the company regarding the prototype for production of ammonia from renewable hydrogen, sorry. So Chen, the floor is yours, if you want to share your presentation.
Thank you very much, Clara. Just for everybody's information, today the presentation will not only done by me, I will do it together with my colleague Jonas, who is a market expert in ammonia synthesis and overall ammonia value chain. By the way, I cannot share my screen. I think you need to enable me to share my screen.
Oh, well. Yeah.
Okay.
Got it.
Yes, I can do that. Let me do my presentation. Yeah, Asia. Can you see my screen?
Yes, you
Yes.
can make it full now.
Yes, I'm going to also share the sound. Sorry, because as ARENHA project consortium partner, I would like to share some videos. So, okay, give me a second. Page 1. Can you see my screen now?
Yeah.
Yeah,
Okay.
you can make it full screen, and that's it.
You got a full screen, right? Or no?
Yeah.
Oh, really?
Good.
Maybe I'm gonna do it again. It says for us, we see the full screen. Second. This one. Now, yes, right?
Yes,
Yes. Yes.
we can see full screen now, yes.
Let's see if I share some. Yes, I do share some. Okay. Good morning, everybody. Thank you for joining this workshop. And my name is Chen. I am the innovation engineer in Proton Venture. And together with me today, I have Jonas. who is our market expert in ammonia value chain. Jonas, maybe you also give a brief introduction by yourself.
Yes, yeah, I've been working for 3 years for Proton Ventures, mostly in market expertise in designing green ammonia production and optimizing green ammonia production to basically try to close the gap between green and gray ammonia.
Thank you, Jonas. So it was our honor to work on this project with all the consortium partners. And today we're going to talk about ammonia value chain from production to application. So who we are Proton Ventures. We focus on ammonia solutions, ammonia innovations, and product developments. As you see here, we have several reference pictures for the storage tank, 30 kg per of ammonia liquid in Bulgaria. We also work on EPC project for ammonia synthesis in Morocco. We also have a reactor design for the DNOx system. So, and regarding the innovation, we work on electrolysis. As you see here, this is a bench scale. This is a basic demo unit we made for Betellizer at the very first beginning. We also organize different kind of knowledge exchange events like NS3 Academia. And beside that, we work on cracker for hydrogen production together with different institute and industry organizations. Of course, we also have a project development. We have more references to share. If you are interested in us, please feel welcome to contact Jonas or me or any of my other colleagues in Proton Ventures. So what we are doing in ammonia in ARENHA. So as Jose Luis already gave us a brief, high-level introduction about who we are and what we are doing, who are the consortium partners. So the idea is to have a power to ammonia, ammonia to power system, which can cater in the renewable energy generation, meaning intermittent energy provision to the ammonia production, and also to achieve the zero carbon emission in the future, which is set by the EU laws. So for Proton Venture, we are focusing on the ammonia synthesis. We don't call it Haber-Bosch because we change the design. And we integrate the chemist option for this ammonia separation instead of refrigeration for liquefying the ammonia. And the timeline of this project has been long. We kicked off the project in 2020, and we finished now at 2025. So we start with ammonia synthesis loop modeling, meaning we do the steady state modeling, we do the dynamic modeling, and also work together with Tujel. And with that design, we are enabled to have a pattern file that has been completed in 2022 to 2023. And since then, we start building and construction and building design and building the advanced ammonia synthesis demonstration unit. As you can see in this slide, we have so many partners who has been supporting us in this journey. We have DTU, Technical University of Denmark. We have CNA2, who support us to prepare the site at Betiberia. And we have our great partner, Demcon sister, Coraltex, Clariant, for providing us a catalyst. We have K-Tainers, who gave us a brilliant logos. And we also have a BBR who made a nice video for us. So without them, we cannot make this demo finish. And what have we done? We have the advanced ammonia synthesis from scratch to the demonstration unit. So now I'm going to show you what it is from the scratch. Please bear in mind that we are in this scope, we are only considering having nitrogen and hydrogen already ready to the synthesis loop. And then we deliver ammonia. So nitrogen delivered maybe from PSA or from cryogenic unit. It depends on capacity. Hydrogen from electrolysis. In this ARENHA project, we are considering an SOEC. And this mixing gas will be compressed to the 80 bar gauge, mixed with the recycled gases, and to the fixed bed reactor. And this bed will be loaded with commercial-based iron-based catalyst that is from Clariant, our great partner. And the produced gases and with ammonia, the produced ammonia with mixed hydrogen and nitrogen will be further separated in the solvent beds. So you see 3 columns here, each of them having different role. One of them busy with regeneration, one of them busy with absorption, and the other one busy with cooling. And this design enables us to liquefy ammonia at a way lower in pressure, and still using cooling water or air cooling for the liquefy for the production of liquid ammonia, and also have a way lower ammonia content to the inlet of the reactor, meaning less than 0.1%, so that can push the reverse ammonia synthesis reaction to forward instead of backward. I'm pretty sure some of you know that ammonia reaction is reversible. So either you produce ammonia or you crack it back to hydrogen and nitrogen. And for the vent gas, as you see, there's a scrubber, so we will absorb all the ammonia before it vented to the atmosphere. This is our demo unit. So from scratch, now this is demo. And to the left side, you cannot see it's a compressor, which has 2 stages, which enable us to compress the gases from 8 bar to 80 bar gauge. And then we have the ammonia synthesis reactor with the heating coil. And we have 3 solvent beds. Now I'm going to show you a video that has been made during our factory acceptance test. So it's not a joke. So because I got questions internally that, hey, Cheng, is anybody acting here? No, please bear in mind, this is a factory acceptance test. Everybody is working on the item that is listed in the FAT procedures, meaning IO check, PNID check, mechanical check, and so on. So that's what you're gonna see now. Okay, I'm gonna play the video. So this is our demo unit. Now I'm gonna give the floor to Jonas, and Jonas is gonna give you more idea about the ammonia market.
Yes, thank you very much, Cheng. So of course, I just killed my question, but it doesn't matter. So I'm gonna give a little bit of an overview of the market, because when we develop these innovative projects with Proton Ventures, of course, we are looking at the options that we have in the market as well, and how we can valorize economically and support the energy transition with those projects. So now I'm gonna ask a question. If you were to have 100 megawatt of solar plant installed in the Netherlands to produce electricity to make ammonia, how long would it take to produce enough ammonia to fill up a 40,000 ton ammonia storage tank? When I first did the calculation, I was thinking, yeah, maybe weeks, maybe months. I mean, you already saw the answer, but the answer is actually 4.5 years. So sometimes we don't always realize how much energy there is actually in ammonia and how much potential it has to balance the grids. And that's why in the very long term, we can see that the market potential is really huge for ammonia in the energy transition. Currently, the ammonia market is mostly driven by the fertilizer and the economic sectors, which is about 200 million tons per year. But we can see that all the growth in the market will be driven by the energy transition and by the new energy users that, of course, are driven by how much energy density there is in ammonia, will be mostly driven by the shipping sector, by the hydrogen carriers, by the power generation. Depending on the sources, the growth of the market will be, let's say, from 3 to 5 times. Here, of course, you see the ARENHA sources that say about 3.5 times increase. But that's just, let's say, the demand side. If we look at the production side, currently most of the ammonia is gray, but we can see that over time there will be a shift towards green. And according to ARENHA, about 80% of the ammonia will be green by 2050. So we can see that long term, the potential of green ammonia is fantastic. And on the short term, there are also lots of catalysts that are supporting this transition. The Repower EU plan is planning to import 10 million tons of green hydrogen to Europe by 2030, sorry, and also produce locally 10 million tons, which if you compare to ammonia, is a total of 100 million tons of ammonia. Of course, it's not just going to be ammonia, but just to give you some orders of magnitude. And then on the consumption side, also, there will be mandates by Europe to consume 42% of the hydrogen in industries as green RFNBOs by 2030 and 60% by 2035. So both on the demand side and on the both on the production side and on the demand side, there will be really a lot of push by the European Union. And at the same time, the competition of green ammonia, which is gray ammonia, will be penalized by the CBAM, the Carbon Border Adjustment Mechanism, which will apply the ETS program to the imported and ammonia produced in Europe, meaning that green will also get a boost. But the European Union is not just applying a stick approach to it, it's also applying a carrot approach to it with the European Hydrogen Bank, which provides subsidy to some of the projects that will produce green hydrogen and green ammonia in Europe. In the last tender, it was up to €0.5 per kilo. And there's a new tender now that has been launched with a budget of 1.2 billion that will support some of the projects that have applied to the mechanism. And finally, there's also H2 Global, which provides a contracts for difference mechanism, which will allow producers to get fixed prices for a long-term offtake agreement. And that will really help financing and support projects to get to final investment decision. The next tender, which has just been launched, has 3 to 4 billion euros in budget to compensate the price differences between green and gray ammonia. So in this context, you would think that everything is fantastic, but the problem is that there is still a cost gap between green and gray ammonia. Depending on the sources, green ammonia is, let's say, between 50 and 200% more expensive than gray ammonia. So how do we close this price gap? And how do we make sure that green ammonia becomes competitive with gray ammonia, meaning that green ammonia can really balloon as it hasn't done so far? Well, we'll look at it, and we'll look at how we can do it, but also how the ARENHA project is contributing to it in the next coming slide. So to understand why green ammonia is more expensive than gray ammonia, we need to come back to the basic economics as to how the cost of green ammonia is being broken down. In general, there are mostly 3 cost components. So there are the fixed costs, the electricity costs, and the capex costs. The fixed costs are about 10 to 15% of the total cost. The electricity costs are, let's say, 30 to 40%, depending on the location. And the capex costs are 40 to 45%, depending on the location. And it turns out that ARENHA is acting on at least 2 of those. First, on the capex side, because if you can operate the loop at lower pressure, you can have a cheaper, better compressor. And also, you avoid all the refrigeration that you have to do on normal loops. And also on the electricity side, if you can run with SOEC, if you can run at lower pressure, you don't need that much compression energy. And therefore, ARENHA is acting on multiple levels to reduce the cost of green ammonia to get it closer to gray ammonia. Now, if we focus on electricity, of course, like the electricity consumption of the loop itself has an impact, but there's something that has even a bigger impact, which is the management of intermittency. indeed, if you want to get cheap green energy, you basically can choose between wind and solar mostly. In some location, hydro, of course, but that's let's say you will not produce all the ammonia in the world with hydro, so mostly you will have to use wind and solar. The problem is that the wind doesn't always blow, and the sun doesn't always shine. And you can see on these profiles that are, by the way, profiles from an excellent location and profiles that are also averaged, that both on a daily basis on the left side as well as on a monthly basis, there are huge variations in the output that you can get from wind and solar. So now, how do you run a process that needs quite stable inputs based on inputs? Based on inputs that are not stable. Well, there are a few levers that you can use. Of course, you can have batteries in the system. It's not the cheapest option, but you can always use it. You can use the grid. You can use electrolyzer mixes. For example, the PEM electrolyzer has more flexibility than alkaline or SOEC, so you can adjust a little bit the ratios here. You can have a hydrogen storage tank. You can have the Haber-Bosch loop, and the ammonia storage tank in a way could also help a little bit to buffer. But if you look specifically at the Haber-Bosch loop, there's actually quite a lot of potential, because if you have the ability to run down the Haber-Bosch loop, you actually have quite big gains in the economics. We've run quite a few simulations in which we have tried to see, based on an intermittent input, if you don't allow the Haber-Bosch loop to turn down at all, then you have, let's say, a base cost of 100 in terms of LCOA. But then if you allow the loop to turn down to 90%, so to turn down 10%, when electricity is not available, you already have a reduction of 3.5% of the levelized cost of ammonia. And then the more you allow the loop to turn down, the better economics you get. And you can get up to 15% gain in one specific case. But like this case is really generalizable, I would say. If you allow the loop to turn down, it turns out that if you are able to run at lower pressure, you have more options to turn down, of course, than traditional Haber-Bosch loops. And therefore, you could gain on the economic side and also contribute to close the gap between green and gray. So now I will finalize with one use case that I think is particularly suited for this, which are islands and microgrids. It's not actually a use case that is like a lot talked about in the media and in the reports, but I think that can really be low-hanging fruits, because microgrids, they are usually not connected to the main grid, meaning that they need to manage the flexibility by themselves. How do they do that? Sometimes they have batteries, but most of the time they are using gensets, which are both extremely expensive and extremely carbon intensive. And you could think that green ammonia production, if you could really follow the curves of solar and wind, you could have a small scale ammonia loop that could also turn down based on this and produce, for example, ammonia when there's a lot of wind and solar, and store seasonally. As we've seen, ammonia can really store very well, and can be given back when the wind is not blowing or the sun is not shining. And from an economic perspective, it actually makes a lot of sense, because when we look at the electricity prices on islands, it's actually very high. On a lot of those islands, they pay like more than €1 per kilowatt hour on the retail market for electricity. If we compare, for example, to the Netherlands, we are paying maybe between 30 and 40 cents per kilowatt hour. So we can see that they are paying 3 times as much because of all the intermittency management, all the gensets that they have to use. When you have such high prices for energy, suddenly a lot of technologies that would not make sense on the mainland suddenly make sense on islanded system. And we can see that green ammonia production, which might not make sense on the mainland, could make sense because the prices are much higher on islands, and a system of small-scale flexible ammonia loops that could be based on the ARENHA system could make a lot of sense on island system. And it's actually not a small niche market. if you look at the global installed power of 8 terawatts, about 120 gigawatts of that is based on small islands that have their own small grid. So it's pretty much 2%, well, almost 2% of the global installed power that we could decarbonize in that way. So yeah, I wanted to give you a little bit of an overview of some market application and some services that ARENHA is providing to the market, which is something that I'm looking at when we're working together with Cheng on ARENHA. Thank you very much for your attention.
Thank you very much. Clara, we will give the floor back to you.
Thank you
Yeah.
very much.
Thank you very much.
Was it? Yeah.
Yeah.
So, thank
So,
you.
thank you.
Jonas,
Yes.
Thank you.
keep talking.
Keep talking.
No, the phone is. If you don't speak, switch off, you mute your microphone, Jane, and when you speak, we close it. So I think they're coming back from them.
Yes, so Jonas and Chen from Proton Ventures, thank you for sharing with us the feasibility of this technology for green ammonia production and all the work you've done during the project. We want to ask people in the room here if they have any question for Proton Ventures, and Francisca from Fertiberia, Paki. We have a question. I think you can talk from where you are. We have a microphone around there.
Okay, if you can hear me.
Can you hear her? Chen? Can you hear
Yes,
Paquita?
yes,
Yeah.
thank you for
Thank you.
the presentation. For Jonas, my question is why nuclear power is not considered for this source, for the source of energy for ammonia production, for green ammonia production, as is it considered in Europe, of course, as a decarbonized source of energy and also as green. And
Listen, yeah, I was born and raised in France, so I don't have an opinion of
the
the nuclear.
efficiency of energy.
So no, I think it's definitely part of the mix. And the problem with nuclear is that developing a new nuclear power plant takes 15 years on average. So for the short-term transition, probably we need to use also other types of energy. I think on the long term, I see a lot of potential for nuclear in Europe because it can provide this base load, and especially if we go to thorium reactors, for example, or smaller scale reactors that are maybe even quicker to do. But I think in the energy transition, we need all the solutions that are economically viable. Nuclear is one, and I think that intermittent ammonia production is also one. And for example, for small islands, nuclear is maybe less of a solution than for mainland in Europe. But I do see a lot of potential for nuclear as well.
And another question is, did you consider the cost of hydrogen storage? Because it is huge.
Yeah, so when I do design those facilities, I basically take an economic optimization based on multiple variables, the hydrogen storage being one of them. And in general, from all the simulations, a small scale, like a very small, I mean, a few tons of hydrogen storage actually does reduce the levelized cost of ammonia of the whole facility. But I agree that pressurized hydrogen storage is bulky and expensive. But if you look at a system perspective, from my experience, it does actually reduce the cost of the whole facility, simply because it allows the facility to run for a lot more hours.
Thank you very much, Jonas from Proton Ventures. Is there anyone else online or in the room wanting to share some comments, thoughts, or questions? No? Okay, so we are gonna take a break, 30 minutes, and we will be back at 11:20.
No, just keep the timing there.
Do you want to keep the timing better?
Yeah,
Okay.
yes, keep the
So
timing,
we will be
because
back
the
at
idea-
1:30, depending on which country you are now. 1:30. 1:30 something, but they- 11 Central European time.
Yeah.
Thank you. See you.
Okay.
Hello, everyone. We are back from the break, and I hope you're enjoying the workshop. We had Proton Ventures before telling us about their ammonia synthesis loop reactor. And we will have now Arrizabalaga. I didn't get it. Arrizabalaga from H2 site. H2 site is the company in the north of Spain who has designed and built the prototype for ammonia cracking to produce hydrogen from ammonia. So Aritz is process engineer there, and you can say hello if you are around, Aritz.
Yes, hello, hi.
Apologies for misspelling your surname.
No worries, I've been called worse.
Do you want to reintroduce yourself?
Yeah,
More fancy
sure.
way? Yeah,
Sure. I'm Aritz Arrizabalaga.
Yeah.
Well, there is a football player with that name that made my life way easier. So, but he's not family. Yeah, so I'm the process engineer and leader in H2 site, and I'm trying to open the presentation at the same time. So, but I'm not very good at doing two things at the same time. So if you bear with me for a minute, I'll open this up and I'll just go ahead with it. Okay, I'm really not good with Zoom or PowerPoint. I wasn't able to
I can guide.
share this
Yeah, so
properly
you have to go to this little square at the bottom with an arrow pointing up.
Yeah.
Yeah,
That-
it's there.
Yes,
then
I managed to do this, and
you
then
have to choose exactly the window you want to share.
yeah, but then I click on present and it doesn't do much.
Wait. There we are. Now you can make it full screen. If you go to the bottom
Yeah.
line, the last square on the right hand side, at the bottom of your PowerPoint.
Yeah, I did that already. But I don't know what you're saying.
It's in the bottom line of your PowerPoint. There is a square.
Yeah, the presentation.
Yeah.
Yeah, I did that. But it's not showing, is it? So you're just saying the open PowerPoint, but not the presentation?
Yes, it's still there.
You have zoom
but-
light bar at the bottom. And
Yeah, the
No,
presentation. I'm doing that, but it's not doing anything
It's
else.
doing this, but I think it's still sharing the window with the PowerPoint.
Yeah.
It's
But
like,
that's not what I see. What I see is the presentation. I don't know what I'm doing. I tried this yesterday and it's not.
it doesn't matter. Yeah, it doesn't matter. You
I'll
can
just try.
you can start.
you have the presentation here. I can move from.
Yes.
One. Solo tiene que hacer.
Está aquí, estoy tan bien, ahí es.
Maybe you, Aritz, creo que tienes que recuperar el modo presentación antes, luego compartir.
Claro, si abro el modo presentación luego no me deja hacer esto, ¿no? Sí, a ver. Voy a probar. Ayer no lo conseguí, por eso lo digo. Vale. A ver.
Ahora.
Okay. All right. Sorry about that. I'm too young to be this bad at computers, but Sorry. Anyways, so yeah, I'm Arit from H2 site. Now the slides won't go. Yeah. So we in H2 site are a palladium membrane manufacturing company. We are the first company in the world to have an industrial manufacturing factory for this sort of membranes. We've got a 2,000 square meter plant in Loyo, which is in the Basque Country near Bilbao, that we inaugurated in November 2022. As I said, we are the first world industrial factory for this type of membrane, and our knowledge is based on more than 50 years of R&D to optimize the manufacturing process. We are a spin-off of Technalia and the University of Eindhoven. That's why we've got more years of research than the company has been existing for. We just turned 5 last month. We are growing quite fast at the moment. We're 60 plus people right now, and this is it's been a bit hectic because I was number 21 in the company just 2 years ago. So you can imagine how fast we're growing. What we do is we manufacture these palladium alloy membranes to produce high purity hydrogen. You can see 99.97% there. That's the fuel cell purity requirement from the ISO for mobility. And we can get that hydrogen purity with our membranes. It's not only about purity, it's also about efficiency. We need to recover a high amount of the hydrogen that is put in contact with the membranes. We go all the way up to 98%, depending on the application. And we are working on very reduced footprints so that it makes sense that this can be done on site of the client. You can see the 3 pictures. The first one, you can see the palladium alloy membranes hanging from a flange. In the picture in the middle, you can see one of our reactors in this case, where the membranes will be installed. And the third picture is one of our skids with one of the reactors in them, with the membranes in them, and on site in their final destination. So what we do is the whole thing. We manufacture the membranes, we design and create the reactors, and then the skids so that they can be installed in the client's facilities for their on-site hydrogen production. We can do this regardless of what kind of raw material we get, all right? We have several different applications that we call purification. If the inlet is already by pure hydrogen, we call that to 98% plus purity hydrogen inlets. So we just put those through our membranes for purification. We can do something similar for what we call separation, which is streams with up to 50% of hydrogen. We work with natural hydrogen as well, which is, as you know, hydrogen that is naturally found in reservoirs underground, very much like natural gas. This hydrogen usually appears with helium, methane, and nitrogen, argon, other gases that are, some of them not very easy to separate for, let's say, state-of-the-art technology, but we can do that as well, and it's fairly easy for us to do. And we are working on gas network management as well, which is just the big natural gas pipelines that are considering injecting a bit of hydrogen in them. Then we are working on taking that stream, separating the hydrogen from the natural gas, and using the hydrogen or providing this hydrogen to our clients, and then reinserting or reinjecting the natural gas in the pipeline. So that's for separation, and then we also do reaction and separation integrated with feedstocks such as ammonia, which is the case in ARENHA, where we do the cracking reaction and the separation in an integrated reactor. We can do that same thing for water gas shift, for methanol, and some others that we're currently researching. Excuse me. The general idea of the reactors is shown in the picture on the right. We can have an inwards flow that you can see at the bottom here. This shows a mixture of different molecules. Some of them, the blue ones would be hydrogen. This would go in a reactor with the membranes hanging from the top flange and surrounded by a catalyst. In this case, you can see that kind of orange color. That would be the catalyst. So the particles that need to be broken down, in this case, it would be ammonia, get in contact with the catalyst, they break down. The hydrogen produced in the reaction gets in contact with the membrane. As you can see here, these small blue molecules would be the hydrogen, get in contact with the active part of the membranes and go through the membranes and then up into the top chamber for pure hydrogen separation, and the rest would leave the reactor on the side. And this is pretty much the core of the technology, and this is pretty much what we do for all of these cases that we've discussed before, with or without reaction. So for ARENHA, we were involved in two main tasks. The first one was to design, construct the ammonia cracker and the membrane reactor. We did this in a structured manner, pretty straightforward engineering. We did the design of the ammonia cracker, we manufactured it, and then we manufactured the membranes. In this case, this task was done by Tecnalia. We used Tecnalia's membranes in this case, and then we constructed and commissioned the whole skid to install the membranes in them. And after that, we sent this to Fertiveria's facilities in Puertollano, where we installed the equipment, where it was tested by Centro Nacional del Hidrógeno. A couple of pictures of what we did. So we designed the cracker in a 20-foot high cube container, so that it could be plug and play, but it would also help contain the ATEX zones. And we did this so that it would be easier to install in some facility that wouldn't require big spaces or being separated from other facilities. In the end, the prototype was installed in a clear area with nothing around it, but this helped us in other ways as well. During the construction, we found some challenges that we managed to overcome. Main thing was that the hydrogen piping and equipment requires high quality welding and thorough testing. We just had to work with specialists in this case, which was a good exercise for us. And then, well, all the testing and non-destructive testing for the hydrogen that is specified in the legislation. A different type of issue that we found was that the best layout, or the best place in the layout for the reactor, was at the very end of the reactor, due to heat integration, which we really wanted to control. But that meant that we needed to remove the whole reactor from the container so that we could replace the membranes in case that were necessary. So we had to install a big beam across the container with a EX-rated chain hoist, so that we could just lift the reactor and bring it all the way to the front of the reactor. Some more challenges that we found that were quite new for me in this case. I have never worked with such a small bore piping, which meant that the valves and instruments were way too heavy for the tubing or piping to take the weight. So we had to calculate all the extra supports, and you can see there is a stupid amount of support around here just to make sure that the weight of the valves wouldn't bend and break the piping. And the final, I think, main challenge we found during construction was the insulation. We're working at around 400 degrees Celsius, so insulation was really important because the performance of our plant depends on temperature control quite heavily, as you will see later on. So after we built this thing, we tested it in our facilities in the Basque Country, and then we sent it over to Fertiberia, where we did commissioning, we did the site acceptance tests with Centro Nacional del Hidrógeno, and we did a training of the operators that would be operating the system. And on top of that, we helped them remotely via our own control room, which we've got in our facilities here in Bilbao, so that we could actually see everything that was happening at Puertollano. I really want to thank Centro Nacional del Hidrógeno because they made communications very, very easy, and that's key for a successful testing campaign as the one that we've had. So the main challenges we found during the operation were the nitrogen pressure, the ammonia composition, low temperature in the separation, and the daily startup and shutdown operations that which we'll discuss right now. So why was the nitrogen pressure an issue? We use nitrogen to both start up and stop the plant, which needs to be done in a controlled manner so that we slowly heat up the whole system to avoid leaks and to avoid damage to the vital equipment of the plant. And we designed this plant to work at 8 to 10 bar because that's the nitrogen pressure that we've got in our facilities, but we didn't know that the available nitrogen in Fertiberia is at 5 bar. This meant that the flow that could go through the system was smaller than it had to be, or than the one that was designed for, and heating took a lot longer than expected. It took around 6 hours, and then we had to stop. So that meant that the heating and cooling of the system took longer than the working day, which could have been an issue if it wasn't for Centro Nacional del Hidrógeno, who reorganized their working hours to work longer days, less days, but longer days, so that we could test during their working hours. This was an issue that we couldn't solve technically, but we solved with these organizational measures. Second big issue was the ammonia composition and pressure. There were 2 sources of ammonia nearby. One had low pressure and high purity. The other one had high pressure, but it was top of the tank ammonia, which means all the volatiles or the gases that aren't pure ammonia gather in that area, and hence the purity of the stream that we had to use, which was this one, was not the design purity, which was 99.99. We had something between 60 to 75% of purity of ammonia during the testing campaign, and the rest was methane, CO2, nitrogen, or argon mostly. We also had designed, as I said, the whole thing to work at 8 to 10 bar, but we finally had to work at a lower pressure because the inlet of ammonia in our system was 7 bar. So the separation had to work at around 5 bar in the end. All this had an impact in performance of the system. And the third issue that had or the third challenge that had impact in performance was the low temperature. We designed a heat transfer for pure ammonia, but this gas had different thermal properties, which meant that the heating couldn't be wasn't the same basically, and we couldn't achieve the 400. We couldn't reach the 400 degrees Celsius that the separator should have been working on at, and instead we had to work at 370 degrees Celsius. So considering the fact that we had a lower temperature, that we had a lower pressure, and that we had less ammonia, because only 60 to 70% of the inlet was pure ammonia, our separator wasn't working at design conditions. So at design conditions, we were expecting to get about 0.9 kilos hour of pure hydrogen. During operation, we realized that we were only getting 0.21 kilos per hour. So what we did was we reverse engineered this, so to say, and we simulated with our simulation tools how much hydrogen we should have gotten at operation conditions. And that's the final column, the column on the right there in that table. And our simulation said it should have been something between around 0.28 or 29 kilos per hour. So we were still a little bit lower than what our simulation tool said. And that's because our simulation tool was out of the usual operating conditions. So we will have to adapt that for these sort of conditions if we want to get an accurate simulation, which we do get when we are in the range of conditions that the simulation tool has been designed for. Okay, and the big issue, the big elephant in the room, was the fact that we had to start up and shut down daily. The system, like most systems that work at high temperature or high pressure, is designed for 24/7 operation, but it had to be operated at 10 hours per day for 4 days a week. So we tried to adjust the shutdown procedure. We couldn't adjust the startup because of the nitrogen pressure issue that we've discussed before, but we tried to adjust the shutdown procedure so that the shutdown didn't cool down the reactor that much. And then the next day we would start off with a higher temperature, and then the heating would be a little shorter. However, this led to membrane damage, which also meant that some of the ammonia could pass through the membranes, and it went all the way down to the vacuum pump that we use to suck out the hydrogen that has permeated the membranes. And the vacuum pump is not designed to work with corrosive agents such as ammonia, and it got damaged as well. So we had to take our operations team down to Puertollano and change both the vacuum pump and the membranes. You can see two of our engineers at work changing the membranes in Puertollano in the picture on the right. So after that, we corrected the shutdown procedure to the original to avoid this issue from happening again, and we managed to start the prototype after that. So several lessons that we've learned from this is that well, we didn't quite know where this was going to be installed or under what conditions was going to work, but we need to be a bit more. We need to be a little less optimistic when it comes to pressure drop or heating capacity, because that has a big impact in performance. So we need to be a bit more conservative when calculating these things so that the system can work at a wider range of operation conditions. The third point we already knew, but it's good to remind ourselves of this, is that the shutdown operation is critical for membrane health. And this is very related to the next one, which is the thermal cycles, starting and stopping every day. So cooling and heating every day. This is really bad for all materials, but especially for the membranes. We saw a reduction of the purity of the hydrogen with thermal cycles. So this is also a good lesson to learn. We shouldn't operate this on a daily basis. We should only operate this 24/7 or in a longer battery of operation. And good positive notes, but it's also good to remind is that everything is easier when you've got a motivated and willing team to work with. And we found that in Centro Nacional del Hidrógeno. So thanks again to all the people involved. And well, the prototype has produced high purity hydrogen for 500 hours, which is I think it's a remarkable milestone for the ARENHA project and H2 site and Centro Nacional del Hidrógeno. So yeah, next steps, we are working on 2 European projects, some more, but I think these are the 2 most relevant at the moment. First one is Apollo project, which is quite similar to ARENHA in our participation. So we're designing work, actually constructing at the moment a ammonia cracker for marine applications. And just so that you can see the jump that we've done in ARENHA towards next steps, we will have the same footprint as we do in ARENHA, but we will produce 10 times the hydrogen in that same footprint. So we've done a 10 times, an order of magnitude jump in production capacity in the same footprint. So that's a big jump from learnings we got in ARENHA project. We will integrate this with fuel cells to produce electricity live. So that's going to be exciting. And we will also be installing this in Fertiberia. So that's good because now we know all the constraints that we've got there with purity and hydrogen, nitrogen pressure. So we'll be ready for that. Another interesting project, completely different to the one that we've discussed before, is we will be designing and constructing 2 prototypes for hydrogen recovery in oil and gas applications, which are really different because hydrogen content in the inlet is very low, and there is no reaction. So fairly different, but just so you guys know that we're working on all our business lines. And we've got a commercial project which we just announced on LinkedIn, I think last week or 2 weeks ago, with Snam, the Italian natural gas and infrastructure company, to produce 100 kilos per day of hydrogen in Italy. We're currently building that as well, and we should be operational by the end of the year or early next year. And yeah, at the path that we're growing, we expect much more to come. So yeah, that's all on my side. Thanks for your attention, and I'm happy to answer any questions you may have.
Thank you, Alex. Do you have any comment or question you want to make? No? We don't have any question.
Well, just a comment.
Comment, yeah.
I hope in the next project in Apollo you will apply all the lessons learned in this project.
Yes. This is Paquita from Fertiberia.
Yes.
Yeah, I recognize her voice.
Recognize.
Yes, we've already included those lessons learned in the design for Apollo. Yeah, that's a good point. Thank you.
Yeah, and thank you for acknowledging the work of my colleagues. They have been working very hard. The some days, very hot days in July, and the cold days in January. Thank you for acknowledging it. It's been a great bidirectional relationship. So grateful to work with you guys.
Yeah, we've got a very active WhatsApp group with action every day.
Yeah. We have a question from Thomas Wood from UKRI in United Kingdom. So go ahead.
Thank you very much for the presentation. I think I know the answer, but from you it would be good to hear. Are you worried at all about palladium supply when you scale up for like marine applications? Is there enough palladium?
Well, no, sorry. Am I worried about ammonia supply?
No, palladium for the.
Oh, palladium supply. Yeah, no, not really. Not really. There is more than enough palladium for the business case that we're working on for the next years. We're not worried about that. We don't use that much palladium than you would think. It's not a worry that we have.
Oh, I think there was a question.
Yeah. Question here. Anyone has a question online?
Yeah, there is one in the chat, I think, by Ellen. I think
He said it has been already replied because she was asking if well, this is Eileen from TNO in the Netherlands, and he was asking if you operate the membranes above 300 degrees, which we already saw that is the case, and she was asking if it's also the case for natural gas and hydrogen applications.
well, there's different applications, as I mentioned, for our membranes, and the temperature that we choose is not only limited or only chosen by the membranes. I know TNO knows a little bit about quite a bit about membranes and palladium membranes. So the higher the temperature, the better they perform, the more hydrogen they can separate. But we have other limitations there as well. Obviously, energy efficiency is one of them, but for the cracking case, you need a minimum temperature as well to make the reaction. So there's lots of factors to be taken into account there. For cases where there is no reaction, and for cases where hydrogen content in the feedstock is small, lower temperatures are favored. Yes, membranes do not perform that well, do not separate that much hydrogen, but if you have to heat the whole system, the whole current up to a high temperature, just to separate a tiny little bit of hydrogen, you're wasting lots of energy. So there's always a balance there, and you need to find a compromise there between capex, which would be number of membranes, and opex, which would be the operation temperature.
Thank you, Aritz. And thank you for your presentation. Anyone else? Anyone? Any question? Any comment? No? So yeah. So that's great. Thank you, Aritz.
All right.
Thank you very much.
Yeah, thank you guys.
Keep up the good job. Bye. Okay, so our next speakers are Vito Verde, who is sitting next to me. He comes from ARENHA, and Valentina Cecchetto from the Technical University of Eindhoven, and they're gonna tell us about market trends and techno-economic assessment of the ARENHA solutions that we are covering here. So let me share the screen. Vito, the floor is yours. Let's see.
So, good morning, everyone. I'm Vito Verde, PhD student at the Eindhoven University of Technology of Eindhoven, and I'm working for ENGIE as research engineer. And today, with Valentina, postdoctoral researcher at TUI, we will give you some information on the ammonia market trends and the techno-economic assessment analysis that we we carried out in the context of our project. So to give you a very short overview on ammonia, ammonia today is one of the most produced chemical worldwide. In 2020, ammonia production was about 183 million tons, and 80% of this demand was designated to the fertilizer industry. Then other applications are plastics, textiles, explosive industry, and refrigeration application. Today, ammonia production process is very CO2 emitting process, which is basically based on the gas reformation, natural gas reformation and cold gasification process for the hydrogen production that is necessary for the ammonia synthesis reactor. And we know already that the current industry path is incompatible with the climate neutrality goals. So there is need to produce ammonia in a clean way. And there are two main pathways to produce low carbon ammonia. First one is the one based on steam methane reforming, so using carbon capture and storage. And the second one is the one based on water electrolysis process, that when using electricity, renewable electricity, refers as green ammonia production. So we know that ammonia demand could reach more than 3 times demand in 2020 by 2050. And in this view, low carbon ammonia could play a broader role in the energy transition, helping to decarbonize the chemical industry, but also other emerging uses of ammonia, like for example, the maritime transportation or the power generation. Today, regarding the market of ammonia, we know that in 2023, 15 million tons of ammonia were traded worldwide for a value of $9 billion. But the important thing to stress is that, and look at the picture on the right, is that ammonia infrastructure for shipping and handling is well developed worldwide in every continent. And so this trading infrastructure can support low carbon ammonia export, enabling also its utilization for new uses. Regarding the low carbon ammonia supply, today worldwide there are like 485 ammonia projects today, and for accounting for total potential production of 450 million tons of ammonia. And by 2030, there is the potential to have operational about 43 million tons of ammonia. And 90% of this production could be low carbon. These data are based on advanced project that has been already recently constructed and in operation, or film project in which final investment decision has been taken, or major projects which are in an advanced state of development. What is important to stress, I want to stress here, is that for the moment, low carbon ammonia projects that are based on natural gas reforming with carbon capture has the advantage. So there are much more projects that are going forward towards a final investment decision compared to green ammonia projects. And the main reason is that there is a high financial barrier, and there is a barrier for green ammonia related to the high financial and operational cost and the low of takers' willingness to pay for this kind of projects. So what we need is affordable and cost-effective green ammonia technologies in order to help to move forward projects forward final investment decision. And this is the reason why in ARENHA we work on new technologies for the whole ammonia value chain. And today we will focus on the economic assessment of the power to ammonia solution pathway and the ammonia to power solution pathway. We run economic assessment in order to benchmark the technology, these new technologies, with other existing technologies, optimize the design and evaluate the economic feasibility, and gain technical insights in order to help making the investment decision. So let's start with the power to ammonia solution pathway, and in particular with electrolysis process. So the question here is why we are working on electrolysis technology. The reason is that electrolysis technologies, compared to other traditional electrolysis technologies, has advantage to operate with a high operating temperature range, ranging from 600 degrees, 650 degrees to 850 degrees. This operation this aspect will imply several advantages. The first one is that thanks to thermodynamics of electrolysis process, it's possible to reduce electrical energy expenditure to run electrolysis reaction, and this translates in higher efficiencies and lower operating expenditures. Then higher temperatures enhances also the kinetics of the electrolysis reaction. So this translates in a more robust supply chain because we do not need precious metals or critical metals like platinum, for example, that is used from PEM technologies. And there is also the possibility of integration with downstream production processes, like, for example, ammonia synthesis. This is a general overview of how solid oxide electrolysis process work. So basically, being operated at high temperature, we use steam for the operation of the electrolyzer. So there is a first step in the process in which water is vaporized and then sent to a heat exchanger network in order to reach operating temperatures of the stack. Then in the electrolysis stack, electrolysis reactions take place, so hydrogen is produced, and then hydrogen is separated from water, unreacted water, and then treated, then compressed and dried. So in ARENHA, we are developing small pilots with a power of 5 kilowatt. But in order to have an effective techno-economic assessment, we want to scale up the system. So the question here is how to scale up system for industrial application, and the reply is through cell and stack development and scale up. This is what we are doing in ARENHA specifically. And the second reply is through modular system approach. So for the modeling of the system, we use the modular approach for the solid oxide electrolysis system. Basically, we have the cell that is the small unit in the system. Many cells are organized in stacks. Then several stacks are combined together, insulated, and combined with high temperature balance of plant equipment, composing a so-called hotbox or SOC stack module. Then many stack modules can be combined together with the power electronics, so transformers and rectifiers and purification and compressor unit in order to build a single repeating block unit. Then many repeating block units can be combined together to have a complete solid oxide electrolysis plant. The technology is scaling fast. We already reached the 4 megawatt scale in industrial project, like for example, the one built in NASA Mountain View facilities developed by Bloom Energy. Regarding the ammonia synthesis process, as already mentioned by Proton Ventures partners, this process is particular compared to traditional one because the separation of ammonia is not done anymore with condensation process, which requires higher pressure and temperature, but it is that carried out using absorption process. This allows for milder operate temperature and pressure conditions for the system operation and leads to many advantages. At first, we can lower equipment costs by 15 to 20% with a comparable energy consumption compared to the traditional small-scale solution. Of course, we won't have CO2 emission because the process is fully electrified, so using renewable electricity, there are no direct CO2 emission. And then we could have also high system flexibility that is enhanced by this milder operating condition. So in ARENHA, we have the interest to integrate these two processes in power to ammonia, so-called power to ammonia processes, because on one hand, we have the solid oxide electrolysis process that is high energy efficiency compared to low temperature electrolysis solution. But we know that this process requires steam, and steam needs to be vaporized, and steam vaporization represents about 20% of the total electrolyzer electricity consumption. So we could use the heat produced available by the ammonia synthesis loop, in which ammonia synthesis reaction, which is an exothermic reaction, is carried out to produce steam that could be directly integrated into the solid oxide electrolyzer. This will offer greater performances and a higher cost reduction potential compared to the power to ammonia solution based on traditional electrolysis technology. So in order to carry the techno-economic assessment, we developed a model, a dynamic model of the whole power to ammonia system, including also a pressure swing absorption unit for nitrogen production and hydrogen storage for the integration of two units because they have different flexibility constraints. And through this model, having as input renewable energy power input profile and defining the system configuration, we are able to evaluate what's the electrolyzer operation and ammonia synthesis operation. So calculate what are the operating expenditure of the systems, the capex related, and the productions of ammonia and hydrogen that then will be used for the economic assessment and the calculation of levelized cost of hydrogen and ammonia production. So to show you some results, here we are dealing with the solid oxide electrolysis system. We modeled a 16 megawatt electrolysis system that is fed by a PV wind hybrid system, renewable energy system. From results with a reference variable that we used, like for example, 50 euros per megawatt hour electricity cost or 60% calculated system availability, we obtained a levelized cost of hydrogen close to 5 euros per kilogram. It is a quite high value at the moment, but there is the potential to go down. And it's possible to notice that the process is both driven by electricity and capex. So both of them represents a potential for lowering the levelized cost of hydrogen. So we wanted to evaluate what's the potential cost reduction if improving technology and scaling up technology. So this is an advantage compared to low temperature electrolysis technology actually, because solid oxide electrolysis technologies benefits of a higher learning rate, so higher potential cost reduction. So we wanted to evaluate what could be this cost potential reduction by changing parameters like cell manufacturing rate, reduced operation and maintenance cost, the scaling up of SOC modules, and the scaling up of the whole system. And we found out that it's possible to reduce capex by 50%, leading to a 30% reduction of levelized cost of hydrogen production. Then we wanted to compare directly the technology potential with low temperature electrolysis technologies, like notably PEM and alkaline. So we consider here this slide is so dense, so there are not all the parameters and assumptions used, but you could ask if you're interested. And basically, we run a scenarios analysis in which we consider a present state of technology scenarios and a possible future state technology scenarios. And as you can see from the graph, there is a minimum. There are at the bottom, is a minimum electricity price of 25 euros per megawatt is considered, while on the upper curves, 100 euros per megawatt hour electricity cost is considered. And it's possible to notice that solid oxide electrolysis technology has the potential to be competitive with low temperature solution, which are depicted by the green and blue curves, especially when electricity cost is high and we could integrate steam into the process. And this latter is represented by the dark red curve. Then we calculate we made the same techno-economic assessment for the power to ammonia solution, so integrating proton venture system with solution proton venture process with solid oxide electrolysis process. We found that we considered here a 16 megawatt electrolysis system accounting for 60 tons per day of ammonia production. And we found out that hydrogen production is the main contributor to a levelized cost of ammonia production, contributing to about 2/3 of the whole cost. And even in this case, system economic is challenged by scale and capex. So even in this case, we wanted to evaluate through a scenarios analysis what could be the cost potential reduction of the technology if we scale up the system from 60 tons per day to 300 tons per day. And we found out that it's possible to reduce levelized cost of ammonia production by 35%. And this could allow for an economic competitiveness of this process with traditional production pathway. In the end, we made some comparison with power to ammonia solution based on alkaline and PEM electrolysis technology. And we found out in this case that SOEC solution is could be more competitive, leading to a 15% reduction in levelized cost of production with electricity, with higher electricity cost. And you can also notice that technologies could potentially be competitive with natural gas, but of course there are some conditions that are required. At first, higher energy utilization of the electrolyzer and low electricity costs from renewable energy assets. And of course, we need to continue research and develop activities on these technologies in order to scale up the technology fast. So that's all from my side, and I will give the floor to Valentina.
Okay, thank you very much, Vito. Valentina, do you want to?
Yes.
Agree, and I stop sharing?
No, you can just keep on sharing these slides, and then I will just tell you when to go next. I think it's the easiest. And so, yeah, good morning, everybody. My name is Valentina. I am a postdoctoral researcher at the Technical University of Eindhoven. And yes, in the ARENHA project, we conducted some studies on a techno-economics as far as the ammonia to hydrogen part of the plant concerns, and I will be presenting them today. Well, what happens when we have ammonia? Basically, the idea is to recover hydrogen that is contained in ammonia via ammonia decomposition through the reaction that you see here on the top right of this slide. So we have ammonia, and through decomposition, it decomposes to nitrogen and hydrogen. This reaction is endothermic, meaning that it is favored at high temperatures, and it also proceeds with increase of number of moles from reactants to products, which means that it is favored at low pressures. So in the conventional system, to recover hydrogen from ammonia would consist of, as you can see on the left side of this slide, of two units: a reaction unit that is working at high temperature and low pressure, and then basically you will have at the outlet of this reactor a stream of hydrogen and nitrogen, and you would need a hydrogen-nitrogen separation unit to recover hydrogen. What we propose in ARENHA project is the use of a novel technology that is a membrane reactor, and you see it here on the bottom right of the slide, in which these two steps basically are combined. So you have ammonia decomposition reaction taking place over a catalyst, and then hydrogen separation takes place in the same device by means of hydrogen selective membranes. In the specific case of ARENHA project, we are talking about palladium-based membranes. If you can go to the next slide, please. I would like to show you what are the advantages. What are the advantages of a membrane reactor? In principle, here are some experimental results. What I would like to show here is that compared to conventional systems, in a membrane reactor, what it's possible to achieve is comparable or higher ammonia conversion at lower temperatures, which leads basically to higher efficiencies of the system. And then, as I said before, this goes with a simultaneous production of hydrogen recovery. So in principle, we have also a more compact system. If you go to the next slide, then please, the question that we would like to answer is the following: is the membrane reactor-based system also economically competitive compared to a conventional system? Because it works from a technical point of view, but of course, then the technology is always, the question is always, is it feasible from an economic point of view? And there are in literature studies that have already calculated the cost of hydrogen production from ammonia. But of course, we would like to see if this membrane reactor technology that we are suggesting actually is competitive as compared to the conventional system. So what we did was a study in which we evaluate what is the cost of hydrogen production from ammonia. And when we try to produce hydrogen from ammonia, for which the final use is direct use in PEM fuel cells. And the final application is for stationary applications, onboard vehicle application, and also refueling stations. In the next slide, I just show the methodology that we use for this study. So at first, we designed the conventional system for green ammonia-derived hydrogen production, targeting the production of 500 kilograms a day of hydrogen, which is basically the typical capacity of a distributed plant. As I said, for 3 different final hydrogen application. Then we optimized the system. So we investigated the operating condition that allow for the minimization of the cost of hydrogen production. And based on the results that we achieved in this stage, then we proceeded with the design of the membrane reactor-based system. And for this, we kept in mind the fact that one of the benefits of the membrane reactor is indeed the fact that it's possible to achieve comparable performance to a conventional system, but at lower temperature. So we tried to design the system at least 50 degrees lower than the optimal case in the conventional system, and working with a similar pressure, operating pressure. And subsequently, basically, what we did was also some optimization of the membrane reactor-based system based on the results that we found based on sensitivity analysis. If you can go to the next slide, then what I would like to show here is what basically how the systems, the two systems look like. So the conventional system, basically, as you can see, is just a packet bed reactor. So let's say a conventional reactor, and at the outlet you see hydrogen and nitrogen. So when you're trying to target the production of hydrogen to be used in PEM fuel cell application, then depending whether it is for stationary or vehicle application, what you have to do is to remove for sure ammonia, let's say the ammonia that is not converted, so the residual ammonia, because in all the cases, regardless of the applications, ammonia concentrations above 0.1 ppm are poisonous for the PEM fuel cell. And then you might also have to remove nitrogen, and this the degree, the extent of this removal depends on the final application. In principle, in the case you want to produce hydrogen for stationary application, you do not really have to remove nitrogen, because in this case, either nitrogen concentrations up to 50% are tolerated, and this is already ensured by the stoichiometry of the reaction. But in case you want to operate for vehicle applications, then you should also remove the nitrogen, because nitrogen concentrations in this case should not exceed 300 ppm. When you go to the membrane reactor-based system, on the other hand, you have the membranes already. So in principle, these membranes make sure that you separate only hydrogen, and with small traces of ammonia and nitrogen. And especially this nitrogen depends, and also ammonia indeed, depend only on, let's say, the goodness, how good the membrane is, because nitrogen and ammonia in principle pass through the membrane only because of defects. So ideally, if the membrane was perfect, you would not need any separation unit downstream the membrane reactor. But since the membranes might have defects, anyway, you can have defects in the connection, in the sealing, you might have some traces, and then you have to remove them. So when it came to the design of this process, we targeted, as I said, 500 kilograms a day, purities of hydrogen of 99.97%, maximum concentration of ammonia of 0.1 ppm, and we chose to perform this study with ruthenium-based catalyst. And for ammonia removal unit, we consider a TSA, so temperature swing adsorption, with a 2-bed configuration. And in the cases in which nitrogen removal was needed, we used a PSA with a 4-bed configuration. If you can go to the next slide, here I present how the conventional process for stationary application looks like. As you can see, we have ammonia being stored, being sent to the reaction unit, and then basically here what we need at the outlet is just a TSA, so for ammonia removal, residual ammonia removal. The process in this case is quite simple, but if we move to the next slide, here I would like to show you how it looks like, what the process looks like in the case we want to work for vehicle applications. You can see here that the process gets more complicated because downstream of the TSA that we had for stationary application, here the stream, basically the stream leaving this unit has to be processed in a PSA unit because it needs to be purified also from residual nitrogen. And then in this slide, you can also see that there is a train of compressors that is required, of course, only in the case we need to operate for stationary application, for a vehicle application for refueling stations. But indeed, like to produce hydrogen from ammonia in a conventional system, the process is not extremely complicated, but there is some degree of complexity. And in the next slide, I would like to present what are the results of, let's say, of the techno-economics, or at least of the economics. We can see that when we calculate the cost of hydrogen for different temperatures and pressures, operating temperatures and pressure of the reaction unit, we see that there is a cost variation, and the cost of hydrogen in conventional system is minimized with the reactor operating at 450 degrees and 5 bar. So this is the optimal operating condition that we select to further proceed. And what we can also notice from this study is that the OPEX, so the operational expenditures, are the ones that drive the cost, the major driver for the cost of hydrogen. And in particular, it is not specifically reported in these graphs, but a big portion of these green bars is given by the cost of ammonia feedstock, because green ammonia is extremely expensive at the moment. If you can move to the next slide, here I would like to show you how, let's say, the process gets simplified when we try to use a membrane reactor. So with a membrane reactor, first of all, it is possible to see a much simpler process even when targeting vehicle applications, hydrogen for vehicle application. And this is because the outstanding performance of the palladium-based membranes allow to remove the PSA unit. So in principle, there is no need for an extra purification stage for the removal of nitrogen. But of course, the need for a TSA is still there because given the fact that ammonia concentration, the residual ammonia concentration that is tolerated is extremely low, a TSA unit is always needed. If you can go to the next slide. Here, I would like to show you also the fact how we proceeded with the optimization. This optimization of the membrane reactor-based system comes from the fact that reactor optimization doesn't mean process optimization. So if we think just reactor-wise, of course, it would be better to proceed with trying to extract with the membranes as much of the hydrogen that we produce as possible. But this might not be the optimal from a, let's say, economic perspective when looking at the entire process. So in other words, a higher recovery through the membranes reduces the available heat from the combustion of the retentate. Because what we try to do, since ammonia decomposition is endothermic, we want to supply the heat through the combustion of the retentate. So what is left behind in our reactor, so what we do not separate. So if the more we separate through the membranes, the least is the, let's say, the heat that is available in the retentate stream, which means that in case this heat available from the retentate is not enough, then we would need to burn more of the products or even more ammonia feedstock, which would make in principle the cost even higher. So the idea was to try to minimize the cost of hydrogen, minimizing the ammonia feedstock that is required by the process. And we found an optimum around, when having a hydrogen recovery through the membranes, around 81%. If you can move to the next slide. Here there are a lot of numbers, but I would just like to highlight some of the takeaways. So when we talk about optimal technical and economic optimum, we do not mean that when you have the economic optimum, you also have technical optimum. And you can see it here when you look at the last row of this table, how the overall plant efficiency varies when we use conventional or membrane-assisted process. In principle, the outcome of this study is that at the economical optimum, actually, the overall plant efficiency decreases when we move from conventional to membrane-assisted process. And in particular, it decreases when we look at stationary and vehicle on board applications. So we go from about 88.7 to 86%, so a little bit, but it decreases. And it just remains constant when we target vehicle refueling stations application. And this is due to the fact that despite the fact that in the membrane-assisted process we use less ammonia feedstock, actually the total electricity consumption in the membrane-assisted process increases. And this is due to the fact that there is a component that is a vacuum pump that is required in the process. If you can move to the next slide. We go now to the economic assessment, and we go back to the question that we would like to respond. So is the packet bed membrane reactor technology competitive or not compared to the conventional technology? And then here I present the results for the 3 different scenarios. So in case of stationary application, actually there is no economic advantage from the utilization of the packet bed membrane reactor technology, because in both the conventional and in the membrane reactor based system, the cost of hydrogen is constant and is about 6.95 euros per kilo. When we go, on the other hand, towards onboard vehicle application or refueling stations for vehicle application, actually then the membrane reactor assisted system becomes more profitable. We have reduction in the case of onboard vehicle application from 7.15 to 6.95 euros per kilo. And what we can see here is that the cost is really OPEX intensive, and 98% more than 98% and more than 96% in the case of membrane reactor assisted system percent of the cost of hydrogen is given by the ammonia feedstock, so which makes it let's say basically the main cost driver. And the similar conclusions can be drawn for the refueling station for vehicle application, just with slightly higher costs, and these are just basically due to the presence of compressors, because in case of refueling stations, we need to increase the pressure of hydrogen up to 700 bars. In the next slide, I want to show indeed, I want to confirm, I want to show that indeed ammonia feedstock is the main cost driver. So if you look at the graph on the left side of this slide, you really see what is the impact of, let's say, variable costs in the process. Let's say when they change, when there is a change in this cost, what is the effect on the cost of hydrogen? And you really can see that the ammonia feedstock is the one that really impacts the cost of hydrogen. For the other costs, for example, membrane, electricity, zeolite, and catalyst, there is an impact, but it's really minimal. So indeed, working in the future towards reducing the cost of ammonia feedstock would be, let's say, what would give the major reduction in the cost of hydrogen. And here on the right, in the same slide, you see what is the forecast. We did some forecast analysis. So these are the costs of green ammonia that are forecasted for 2030 and 2050. And based on this, basically, we calculated what is the expected cost of hydrogen. So you really can see that it is expected that between from 2020 to 2050, the cost of hydrogen from green ammonia could reduce from 6.95 euros per kilo to 2.90, which is quite a decrease. And then if you go to the next slide, I think we're approaching the conclusions. Yes, I would like to summarize the results of this study. So in a membrane reactor for hydrogen production from ammonia, technologically higher efficiency and compactness compared to a conventional system are achieved, and also fuel cell grade hydrogen production is possible. And this is just possible with the addition of a relatively simple and inexpensive sorption unit downstream of the reactor. And from an economic point of view, the recovery of hydrogen from green ammonia can be achieved with membrane reactors at lower costs as compared to the benchmark technology. And this, of course, leads me to the final conclusion, which is that the membrane reactor technology holds significant potential in advancing the decarbonization of the current energy system. And with this, I conclude my presentation. If there is any question, I would be glad to respond. Thank you very much.
Thank you, Valentina. Let's see if anyone wants to ask something about your presentation. Let me stop sharing. And Francisca.
Vito and Valentina.
From Vito and Valentina, sorry. I will stop sharing. Yes, so we can see you here and we can see Vito as well on the main screen. Francisca Paquita from Fertiberia. She has a question for you guys.
Yes, mainly for Valentina. Thank you very much for the presentation. It's very interesting. And I would like to bring up an issue. I don't know if it's in the core of ARENHA, but for us it's very important. It's the safety of ammonia use, using it as an energy vector. As you know, ammonia is very, very toxic. It's compared to the rest of the gases as fuel, which are not toxic. Ammonia is very, very much. It's a small percentage of ammonia is lethal. So it is under the umbrella of Seveso standards. So to use it as an energy vector, I have many doubts, because we cannot store it at a capacity higher than 25 tons. So I cannot see it as in a fuel station, for example, close to some population, places, schools, highways, etc. It's impossible because of the special standards. So I only can see it in a standalone place with big tanks and big cracking unit and so on, compared to ammonia factories or installation as our factory here in Puertollano. What do you think about that? If it's in your core, did you study it? Because in other projects, we are very, very much concerned about safety uses.
Yeah, thank you very much for your question. I agree with you. Of course, it's not something that goes with an easy fix, and in a way, of course, we cannot discard and we cannot just say, okay, it's fine to use ammonia and let's use it as it is, no problem. My point of view is that yes, it is dangerous, but in a way, it's also a matter of don't take me wrong, I will say it and then I will explain further. It's also a matter of social acceptance in a way. And then starting from this, I think that we should, I'm not saying that we are ready to go for it immediately, but on the other hand, in these studies, what we try to do is not to say we go on big scale. What we're trying to do is we go with decentralized, and then we would not have big tanks to run for, let's say, 3 months. We would work with relatively small storage of ammonia and then refill it every few days. So we would not have big tanks. The idea would be to produce hydrogen in a decentralized way, so not producing too much. Okay, in this case, we said 500 kilograms a day, which is not very little, but it's also not a big plant. So, I mean, yeah, I agree with you. On the other hand, we need to start somewhere. And then when we talk about refueling stations, yeah, then the discussion is a bit, in a way, different, in the sense that what we are trying to do is to produce hydrogen, and this hydrogen has to be used to refuel cars, for example. So in a way, we are a bit wasting, in a way, the potential of our technology, because we use hydrogen to produce ammonia and to basically avoid the storage of hydrogen. And then if we try to redecompose it and store hydrogen, then we put the problem back. So in a way, we render a bit useless our process. But in a way, I mean, I think that if we should start from small projects and then improve from there. But I totally agree with you that in a way, yeah, there are very big safety concerns on that.
Maybe I can add something else. I don't think we are going to use this in the city.
Yeah.
That's the first point. That's the first point.
Or in the harbor, like Rotterdam.
No, in the harbor there is receiving, you are receiving ammonia in harbor now. I don't know what they have to fulfill some safety situation. Depends on the population, maybe there are some preparation. They have to, but they have to fulfill, they have to fulfill this. But you have in the maritime transport, okay, you are the water. It's a good thing to finish the new guidance. Last at the end of last year was some guideline for the maritime transport using ammonia, and you have also solar plants that are not located. They are in the land. They are not cities, maybe like Fertiberia regarding Puertollano, something like this. And you also have refueling stations that are not located in and also industries for having hydrogen and so. I think there are some places that it could be a possibility, but for sure I don't think
Fuel station, for example.
But there are fuel stations that they are not in the cities. They are in the motorway, and they are. You can have some pipeline. You can have the size is not so big for a storage station. You can have and then it's also a thing of the cost. It's more cheap to transport ammonia than transporting hydrogen or things like this. So maybe you have the photovoltaic is 105 meters away the refueling station. You have the tank, and then you have the cracker there. So I think it's a matter to see what are the safety. I'm not talking in a city or near a village. I'm talking something that in the way you go by the waterway, they are empty, they are the land around. So it depends what is the situation, but for sure I don't think that in the city it's possible, because we're already having ammonia has been transported, but we don't know what is the runway in the train, and we don't know this ammonia is coming by train because you have chemicals also. So I think it's true what you say, but there are applications where you can consider to pump ammonia. I think so. That's my opinion.
Yes, but for example, in Netherlands, it's not allowed to transport ammonia by road or by train because of the population. It's very dense.
Yes.
So if there's an accident, it could be lethal.
Yeah, they do the cracking, and then they have the pipeline for the hydrogen. They're doing a backbone of hydrogen because they want to have villages with hydrogen as well. So and then there are different situations. They receive in the port, they do the cracking. They have the backbone with the industries that are near the place where they have the cracking, and they distribute by pipelines. And I guess they're doing also, I know there were some cities that were doing also new pipelines for having hydrogen instead of using the natural gas grid. So at the end, everything might be 20 years, 30 years, everything will be more connected and now with hydrogen pipeline. They have other concerns, they are not as toxic. Well, I don't know, like corrosive and ammonia, but you don't see this is a flame, you don't see for the hydrogen. That's another issue.
But the difference is that ammonia is not only inflammable, but also very, very much toxic.
Yeah.
So
that's just, yeah, but it's
the main issue.
yes, it's the toxicity. But I see when there's too much that very dense population, you have to fulfill the rules, and for sure there will be. I think will be decentralized cracking, and then but also ammonia being transported from.
Okay, do you have any other question in the room? We have a question,
So for the final, that would be more for the end. Yes, there was a question, and okay.
it's a question from Jesus Martin from the.
I will read. There are many questions. There are many questions there. First, congratulations to the ARENHA's consortium for the results achieved by the project over these years. I have several questions. If you were to start a new project, ARENHA 2, tomorrow, as a continuation of this one, what main challenge would you propose as a follow-up to the ongoing research in the ARENHA project? Second question, what would you do differently in your researches based on what you know today compared to what you initially planned in the project? And three, at what technology readiness level do you think the project has reached for each prototype? Is what you thought initially in the project? I will is I don't have limits of money, because at the end, the next step is to build bigger prototypes and also to have long-term tests. Because and this means costs. If you increase the size of the prototypes, maybe you have to have a project only in ammonia cracking, or also another line is to combine electrolyzer with the ammonia synthesis unit. For instance, it has not been tackled directly in the prototype in the project. That could be another thing to look at. But it's the size, long-term duration tests. It's true that we have the phase 2 situation to change the testing place for the prototypes for the ammonia synthesis and ammonia cracker. So instead of having shoot on and shoot off every day, having 24 hours, 7 days, or at least 24 hours, 5 days, having the weekend stop, but it's already a good time to test running the system. But I would do with bigger prototypes for sure. And I will integrate in for sure also the solar dioxide electrolyzer with ammonia synthesis as well. But I don't know, we have to learn, we have learned many now for the cracker prototype, we will say. I know the other project are going to with 100, 150 kilograms per day. So there's already one magnitude. But then to increase the TRL, you have to have long-term tests and see that's for me the business state. To move to TRL 7, I think here we have arrived maybe TRL 5. That was the target. No, in all the lines, because the catalyst, and then we use a commercial catalyst. It was planned for the cracker, for the synthesis. We were planning to have a new catalyst, but there are partners, there are other projects where we develop catalysts for ammonia synthesis. So that's also in another project. This is ongoing. And the main point is to have in all the projects, all the value chain able to produce, to manufacture in a higher scale. Because sometimes you develop a small amount of catalyst, but then you want to increase the size of the prototype and you want to go to the market. If you have only university, you have to incorporate the company, the catalyst company. But this applies also for the reactor, for everything, because if you want to go to the market, you want to sell the systems, first you have to demonstrate their viability, a more bigger scale and timing, and then have the supply chain that allows you to sell, to increase the size, and because I think this is that is not. No commercial prototypes, 10 kilograms, that's nothing. You have to go maybe minimum 300 tons, something like this, for ammonia production at least. And then you have to have all that is very important, because in some cases, the project, you don't have at the beginning partners that are coming from the industry able to have this, to do this study up. You cannot. increase the TRL of the systems and have them do the explain. So then who is providing me this? The catalyst in this amount for whatever components. But I will go in this good direction, but I think if you go to big scale, you have to go have a big budget. You want to deal all these things we have done on the prototype side, we are considering here. I will say these things. I don't know if that so I'm happy with the result of ARENHA, I would say. Because okay, we need to do some testing, more testing, but I think the results are interesting. I know so in solar, we know from the solid oxide electrolyzer from IKTS, there's already someone who's going to the biggest scale of the production of the cell and then to have a stack. It was 8 megawatt production, and so that's a good step. H2 site is committed to also to go to the big scale production. I don't know if they were talking about 3 or 1,000 tons or something like this in 5 years. And this I know this is a market. This is the market content as well. And so that is a very important point to do for the development. But there are still things to be done too. For me, it's long term, but 8,000 hours, something like this. Because at the end, when you have centralized, it's different because is decentralized, it could be more small, but it's a way to demonstrate that okay, maybe it's possible to go to a bigger scale when we do some small scale. And because at the end, you want the plant to be there 30, 40 years. Who is going to invest on something that you have not been demonstrated 8,000 hours or more that could run? That is the other people to go to a bigger scale and to go to more. Don't need I have replied to Jesus. But for the project, we're dealing with many things. I don't know because we're on ammonia, green ammonia synthesis, and also green nitrogen synthesis. So, but it was more long term than from the prototype application.
I'm gonna ask. Anyone wants to ask any other question or comment or anything? Otherwise, I would ask Emilio Nieto, our director, to come and please close the session. You have a seat here.
It's not necessary. I prefer to stand up. Don't worry, it's not
Here on the camera
with the formalization. Thank you to all. Thank you to all you are here in order to hear that. Thank you, the speakers, and also the people who are not here. I hope the next time you will have the opportunity to travel to Spain and to visit us. Also, thank you to the Commission. I think it was also a trust from them in order to allow us, in order to have this system project, in order to develop and try to demonstrate that the ammonia could be one of the energy vectors in the future, not the only one, because I think one of the main conclusions is that we need to be open in order to show the different solutions available in the market and how it's possible to profit all of them and to go in the neutrality. And this is something that we need to go further. I'm happy because I'm following with you the coordinator of the project, Jose Luis, because I think the results are quite good. And the most important for us is that I think we are having a good collaboration and cooperation between all the partners of the project, and this is the first step. I think we have a very good connection and integration in order to continue working further and of course to cover the next steps. Always we are asking for money, of course, but the public and private partnerships is absolutely necessary. And what we have to do is how it's possible for us to increase the size in order to offer the solution to the companies. And I'm completely sure that in the future we will have some possibilities. Also, I'm happy to cover all the different temperature range, let's say. I think it's one of the, I'm not saying the unique project, but this is not so often to have a project with a competence within the partnerships. And we don't have face any problem in order to work with the low temperature and also the high temperature technologies. And this is something positive because both technologies needs to be developed and needs to be applied in a high volume in order to cover the needs on the industry. So for us in the National Center, is very happy to receive you here. I think you have now a visit, please profit the visit, even if it's a high-speed visit, let's say, because we have not too many time. Some of you need to pick up a train to come back home. But in 1 hour, I hope you will have the opportunity to visit the facilities we have and try to see the different prototypes and the different projects it has been running. Also here, it's not only concentrate on the ammonia, but also with the hydrogen scope. We have a lot of different projects and different possibilities for you to see. And later on, I think we have a quick lunch, more quicker than the visit, I think. But it's only to have some network possibilities. So for me, it should be a pleasure to be here. Thank you for the meeting. That's okay.
Yeah.
Thank you. Okay, so ciao, bye bye to the people outside.
Thank you, Shan.
Thank you very much.
Thank you, Valentina.
Thank you.
Thank you. Bye
Bye.
bye.
Bye bye.
Bye.
Stefan, already the train.
Bye, Stefan. Good trip back.
Connection.
Antes la visita ahora y luego ya cuando vayas a